Thank you.
Thank you. As mentioned, my name is Mousa Arraf. I'm from the University of the Technion. And today I'm going to present our work, CIQA, a coding-inspired question answering model. Let me start with a quick background. So the problem we're trying to attack here is answering complex questions that involve multiple entities. And as you know, attacking such questions would necessitate a deep understanding of the involved entities, the interactions between them, the state transitions, and their interactions. For example, you can look at the first example we show on the left from the dataset we curated. It involves two entities, at least star A and star B, and an observer that's standing on Earth, which is supposed to observe some interaction between the two bodies. Another problem with complex question answering is that not always we would have all the knowledge we need to answer the question within the context itself. So we need to introduce a domain-specific knowledge, domain-specific information in a controllable way and a reliable way that would prevent hallucinations. So for example, if we look at the bottom example there, we would need to understand the protein sequences flexibility, which is a biology native knowledge that needs to be understood by the model. So both of the challenges we're trying to solve are summarized here, which is tracking multiple entities, logical reasoning over the entities and their interaction, their state transition, and introducing external data to the model that we can change dynamically and reliably. So our methodology builds upon a previous work we did, where we chose to represent the natural language question as a logical representation using a code, where executing such code would return the desired answer, where the logical representation actually enforces the logical reasoning within the question answering model. And it would allow more interpretable and more nuanced understanding of the question. The introduction of new information into the question answering model we propose to do by incorporating API usage within the generated code. By doing this, we allow for the injection of information at inference time, where the model doesn't need to know all the information beforehand, like at training time or before. Like the use of an API would allow the model to tap into the knowledge bases that are available and updatable always. Okay, so our architecture is composed of two main components. The first component is the coder model, which is essentially a natural language to code generative model. We relied for this component on a pre-trained natural language to code generation models. And our architecture also involves another component, which is the API attention mechanism, which helps direct the code generation model into using APIs without extensive reliance on aligned knowledge. So for this architecture, we can leverage, for the API attention mechanism, we can leverage external sources and help the code generation model in using APIs in a case-sensitive manner. So how we trained our model. So as you can imagine, there's supposed to be a series of steps in training such a model. The first step we propose doing is introducing the new API tokens into the code generation model. What we did there is that we manually introduced a new token per new API that we want to introduce into our model. The second phase is we wanted to train our model to generate code as an intermediate representation. It's not an instruction following of generating a code like a normal text to code generative models. And the last step, we train the API attention mechanism alongside with all the ecosystem such that it would work harmoniously together. Training an LLM, it's not an actual LLM, training a language model to use APIs we chose a pre-trained code generation model, more specifically a Radinsky model, which includes 77 million parameters only. And we introduce new tokens per new API that we want to introduce into our code generation model. We train the embedding layer of said model using BERT for masked language modeling on collected snippets from open source repositories, where the model can learn in an unsupervised way how to can learn a representation for these APIs in a case-sensitive manner, so it would understand the context where the APIs are used at. For training the API attention mechanism, we used the formal documentation of each API that is published alongside each API. And in this way, we resemble how coders 10 years ago maybe actually developed code where they resulted to the documentation. And using this documentation, we could measure how the relevance between the case scenario of the question and the use case the API can be used at. After computing the similarity between the two, we passed them through a fully connected layer, where at the end of it we obtained a probability vector over all the new APIs that we're introducing. And we used that probability vector to manually tweak the log probabilities of the next token that is being generated by the coder model. That way, although the model knew it is supposed to use a new API, but in this way it knows it is directed into the correct API from the correct field. Training the model to generate code as an intermediate representation was trained in two phases. The first phase, which we call the sequence-to-sequence phase, where the model was trained on a natural language question as input and the expected target code as output, and we try to maximize the likelihood between the generated code and the reference code. The idea behind this is that we wanted to treat the problem as a translation task more than a question answering task. So the model would learn how to think using code. After the model knew how to generate code, the problem is after the first phase, the model wouldn't be aware of the small lexicographical errors that it's doing. For example, it could use addition instead of multiplication. So what we propose to do is that we use reinforcement learning on the generated code, not the generated code, sorry, but on the return value of the generated code against the reference value. When in this phase, the model didn't have any access to the intermediate code. It was only measured upon matching the exact answer in the output. As baselines, we used a relatively small language model, which is only 77 million parameters, called Radinsky. For comparison, the new language model are tens of billions of parameters, so it was really relatively small. We did experiment with larger coder models, but we didn't notice a significant increase in performance. We compare our model against code generation models, which are simply code generation model without the new training method, and against foundation models, and which were trained and untrained in both cases. We use for the code generation models Code Llama, CodeGen, and GPT-4. As for datasets, we wanted to show that our model can adapt, or our architecture can adapt to multiple domains, so it's not restricted into a known set of APIs. So what we did is that we developed 3 datasets in 3 different fields: astronomy, biology, and chemistry, where for each of those, we compiled a set of a few hundred APIs that are used in those cases, that are useful in those scenarios. And we showed that our model, our API attention model, could actually route the code generation model into using the correct API from the correct field. Our results show that this model, although with Marian CG, it is superior to all the foundation models, state-of-the-art question answering model and text-to-code models. Although, if you notice, with CodeGen, with 350 million parameters as a coder model, we didn't notice a significant increase in results relative to the amount of values we to the result. Thank you. If you have any questions.